Hello, everyone. This is Mr. Smith. Glad to have you back. Today, we're going to try to work through some balanced equations, kind of in a different way. So we're going to use the website Chemthink that I like quite a bit. So I'll put the sim bucket link into you, and that'll bring you to this page here. You'll open this up, and then you're going to type in your name into the guest name. And when you're done, not only the tutorial, but the problem set, you can copy and paste that successful page into the Edge Elastic, and then you'll be set. So go to tutorial. And so 30 slides, I'll go through this with you, and then you can try it again on your own. So we're going to get 3 different reactions here. I'll move this out of the way, perhaps. Okay. So reaction 1, you have kind of brown and green. First they're apart, and now they are together. So that's a creation of a new bond. Here we have this kind of fairly large, relatively large molecule. Now that it's split into different parts, we have broken some bonds. That's a decomposition reaction, which we'll talk about later on. Today it's going to be focusing on the balancing. But do notice how you have the same number of atoms as a reactant and as a product. And here we have the gray with the light green. Now we have the grays together, and the light green found the green. So some bonds were broken, some bonds were made. But again, all of the individual color circles have the same number of atoms before and afterwards, and that is definitely a balanced equation. So all 3 reactions involve rearranging chemical bonds. Chemical bonds involves breaking bonds, creating new bonds, or both. So again, synthesis, decomposition, and some kind of replacement. But beyond that, it's all about making and breaking bonds. So for this first reaction, the red and green dots are the reactions. So when they're apart, we have reactions on the left-hand side of the arrow, and then they're the products on the right side of the arrow. They are now together. So again, left-hand side reactants, right-hand side products. Products are produced, reactants react. So here's some words. Reactants are the materials before the reaction begins. And again, the noun is reactants, the verb is react. And then products are the materials after the reaction is finished. Again, the products would be the noun, and produced would be the verb. Products are produced. So when we write down chemical equations, we usually don't draw pictures, although it is kind of nice to kind of see it. But we do tend to draw our elements using our periodic table. So Fe and S apart, and now they come together. And then here are the T-charts we've seen in the past couple of lessons in terms of balancing the equations. And that's true for fairly simple reactions and then fairly complex reactions. Calcium carbonate, your bone, decomposing into calcium oxide and carbon dioxide. Again, this T-chart will help us show off that they are balanced. Notice that equal sign has some intent to it. And then this last one is another chemical reaction. Again, all of these are balanced. You have 2 hydrogens in, 2 hydrogens out, 1 magnesium in, 1 magnesium out, 2 chlorines in, 2 chlorines out. Balanced chemical equations. All right, so what about forming water? Well, kind of the same concept, except if you just kind of go at it without thinking about balanced equations, it's not going to work. And so here's diatomic hydrogen, diatomic oxygen thrown together to make water, and there's just leftover oxygen out there. But that's not what happens during the chemical reaction. The only product is water, not just this monatomic oxygen. So we need to do something to account for this lone red dot over here. And so what actually happens is these are my reactants, and then these are going to be my products. Now, where do these coefficients 2 come from? That's the intent of balancing these equations, to make sure that whatever goes into it comes out of it. And so here's a little scale to show this off. Here's copper and oxygen making copper oxide, copper 2 oxide. But notice there's 1 less oxygen. So 1 oxygen can't just disappear according to the conservation of mass. And so we need to balance this in a way so I have the same number of each atom before and afterwards. And so you drop in 2 copper oxides. Now that gives me enough oxygen count up the red dots, 1, 2 coming in, 1, 2 coming out. But now I have one copper coming in and only in more than one, two coppers coming out. And so that's not balanced. And so now we need to keep going, drop in another copper atom with the coefficient 2 here. Now I have two coppers in, two coppers out, two red oxygens in, two red oxygens out. So when you balance these equations, you have to kind of play around with educated guesses, educated checking to put those coefficients the way they need to be. So here's another one, the combustion of methane. And so definitely doesn't balance with one of each molecule. One is the default, zero is not an option. Notice you have four hydrogens coming in and only two coming out. So you can see the four gray dots here and only two coming out. Oxygens aren't balanced either. So we kind of just keep doing things one at a time, drag the molecules to make this happen. So at the very least, again, we have one of each. Zero is not an option, even though I guess that's the starting point. So carbon is satisfied, but not hydrogen. So I tend to start left to right. So I have four coming in, and only you can see the four grays coming in, two gray hydrogens coming out. The only place to get two more gray hydrogens is by bringing another water molecule. So I do that, and when I bring in that other water molecule, I have two, a coefficient of 2 as opposed to a 1. So I think in the past I've been showing you to change the coefficients and watch the molecule come. This is a bit of the opposite logic. Bring in the other molecule and watch that coefficient change. So four gray hydrogens in and out. Now I can look at my carbons, one black, one in, one out. Now I need to work on my oxygen. So I have four red oxygens, these two reds and these two reds, and I can see that up here. Two distributes to the one here, so two red oxygens over here. That one distributes to this O2 here, so that's two over there. 2 plus 2, this plus sign is a literal plus sign. 2 plus 2 is 4. I only have 2, so I need to bring in 2 more. I can only bring in them as sets of 2. Now that I have 2 diatomics here, I need the coefficient 2 there. Nice work. Moving on. So here's another reaction. Again, at the very least, we have one. My reactions go over here. I don't think it'll let me bring it over here. Nope. Which is good because that's not how it works. Notice it's unbalanced. I have 2 nitrogen atoms going into the reaction, only 1 coming out. 2 purple, 1 purple. So the only way to get the purple is by bringing in a whole other nitrogen trihydride molecule. And so my nitrogens are balanced, but my hydrogens are not. 2 times 3 is 6. You can count out the 6 gray circles over here. There's only 2 over here. They come in 2s. So bring in another one. My coefficient jumps up to 2, but I only have 4. 3 times 2 is 4. So bring in one more. Set of 2, one more pair. Now I have 6 gray hydrogens. 3 times 2 is 6 gray hydrogens in and out. So we have balance of the reaction. So without actually drawing the circles, there's other ways to do this with that T-chart. And so you can manipulate these numbers. And so I'll do that with you. Potassium looks good, chlorine looks good, oxygen not so much. And so a 2 and a 3, since they don't go into each other evenly, you have to look for a common multiple. So the common multiple of 2 and 3 is 6. And so I'm going to jump this up so I can have 6. Now when I change this, that becomes a 2 and then a 3. I want 6 on the other side. By only clicking it once, I did that before as well. So now I have 6 oxygens in, 6 oxygens out. But now I have unbalanced my potassium chloride. If I change this coefficient from 1 to 2, now I have 2 potassiums in and out, 2 chlorines in and out, 6 oxygens in and out. Nice work. Let's try another one. We actually balanced this the other day in class. And so my aluminums aren't balanced, and now they're on my oxygens. So I can change my aluminum 2 and 2, but that doesn't do anything for my oxygens. So I need, again, to look for these least common multiples of 2 and 3, which is 6. So I'm going to jump this up to make it 6 each. So now it's 3 and 2. I just have to fix my aluminum. So I need 4. I have 4 coming out, so I need 4 coming in. Up, and now we're good. And so this all relates to the the conservation mass, which allows you to change the coefficients not the individual subscripts. So be careful with that. You can't change what the chemicals are. I couldn't go back here and change aluminum oxide to be AlO2 just because this is an O2 in here. Remember, bonds are made and bonds are broken. So we have new properly crisscross ionic formulas here, and I can't just change them because of what preceded. And now that I did that, I have to balance it again, but I do remember the answer. There we go. Um, and so after you're done these 30 slides, you're going to return to the home page and go through these problems. You have to get 10 right before you get 3 wrong. Otherwise, it'll restart the problem set. Pay attention to it. Some of these are check all that apply. Pay attention to what was right and what was wrong so you don't make the same mistakes again, so you get the same successes going forward. And so you can do this. Just hit continue, and then it'll load into you. And I click continue too fast. But which of these are balanced chemical reactions? You're going to have to be able to count up these colored circles. So here I have 2 red coming in and 3 red coming out. That's not balanced. Here I have 2 of each. They've rearranged. Bonds were broken and bonds were made, but they were rearranged, but still 2 blue in, 2 red out. Over here, looks like I have 4 red in and 3 red out, so that is not balanced. Over here I have 1 red in and 3 blue in. Here I have 1 red out and 3 blue out. Again, they're bonded differently, but they're still accounted for. And so that was an example for you. So keep doing this until you can get 10 correct. I wish you well. Remember, chemistry is everywhere.